before the first atom formed, before light could travel, before time itself began to tick. There was something, or, more disturbingly, there was nothing. And that second option might be the most frightening idea science has ever faced, because if the universe came from absolute nothing, then nothing has to actually be something, and that something is far less stable than we think. But before we get there, we need to start somewhere that seems almost boring by comparison. Alright, let's go. Number 10. The quantum gravity seed. In 2006, Martin Bojewald at Pennsylvania State University applied loop quantum gravity to the moment just before the Big Bang. The math showed something unexpected. Instead of a point of infinite density, the equations describe a universe that contracts down to a finite, incredibly dense state, about 10,000 trillion times denser than lead, and then rebounds, like a spring being compressed until it has no choice but to explode outward. What makes this impossible is that general relativity cannot cross that boundary. The equations break down at the singularity. But loop quantum gravity doesn't. It passes right through, describing a universe that existed before our Big Bang, shrinking instead of expanding. And that's not even the terrifying part. The real implication is that our universe may be just one heartbeat in an endless cycle of collapse and rebirth. But if that's true, what was the very first heartbeat? What started the cycle? We'll come back to that question with number 3. Number 9. The cosmic bounce from conformal cyclic cosmology. In 2010, Roger Penrose and Vahe Gurzadian announced they had found concentric circles in the cosmic microwave background, patterns of temperature variations so precise they should not exist in a single bang universe. The circles represent gravitational waves from supermassive black hole collisions that happened before our Big Bang. These waves survived the transition. They passed through the end of the previous universe, through the Big Bang itself, and imprinted themselves on our sky. No known model allows information to survive the death of a universe. The CMB is supposed to be a snapshot of our universe at 380,000 years old, not a fossil record of something older. Here's where it gets disturbing. Penrose's model requires that at the end of time, when all black holes have evaporated and all matter has decayed, the universe becomes a sea of massless particles. In that state, scale loses all meaning. A universe filled with nothing but light is mathematically identical to a universe at the moment of the Big Bang, so the end becomes the beginning. But what happens to information when all mass is gone? Does it just loop forever? And that connects to something we'll get to in number 6 that makes the question of information even stranger. Number 8. The string theory landscape. In 2003, Leonard Susskind and the string theory community proposed that our universe is one bubble among an infinite foam. The math of string theory allows for 10 to the 500 different possible vacuum states. That's a 1 with 500 zeros. Each vacuum state produces a universe with different physical laws, different particle masses, different forces. Our universe is just one bubble in this cosmic foam, and before our bubble nucleated, there was the foam itself, a higher dimensional space where time and causality don't operate the way we understand them. The impossibility here is profound. These other universes are not simply far away, they are permanently disconnected from us. You cannot reach them. You cannot see them. The mathematics says they exist, but causality says you will never have evidence. What no one talks about is what this does to the concept of probability. If every possible universe exists, then the word rare has no meaning. Everything that can happen does happen, an infinite number of times. Your life, your choices, every decision you've ever made, it's all been played out in every possible variation across the landscape. So why do we find ourselves in this particular universe? That question has no answer within string theory. It just is. Number 7. The black hole hologram. In 2022, Eric Verlinde and his team at the University of Amsterdam published a derivation of gravity as an emergent phenomenon from quantum information. Before the Big Bang, they argue, the universe existed as a two-dimensional hologram, a surface encoding three-dimensional reality the way a credit card chip encodes your bank balance. The energy density of that pre-universe state was not infinite. It was zero. And yet it contained all the information needed to generate 100 billion galaxies. That shouldn't be possible. Zero multiplied by anything is still zero. But in quantum information theory, information is not energy. You can have infinite information density at zero energy, and that's exactly what the holographic principle predicts for the initial state. But the part that should concern you is this. If our three-dimensional reality is a projection from a two-dimensional surface, then everything you see, your hands, this room, the stars, is an illusion in the most literal sense. The real physics is happening somewhere else, on a surface that doesn't even have height, and we are just the shadow, a shadow that can think, a shadow that can ask why it's a shadow. That leads directly to number 5, where shadows become even more unstable. Number 6, the eternal inflation remnant. In 2012, Alexander Vilenkin at Tufts University calculated the probability of a universe like ours emerging from the quantum foam of eternal inflation. His result, 1 in 10 to the 254. But here's what he also found. Eternal inflation has no beginning. The inflationary field that drove our Big Bang is a quantum field that, once it starts inflating, never stops everywhere. It stops only in patches. Our universe is one such patch, but the inflating background itself is eternal into the past as well as the future. Before our Big Bang, there was this inflating sea of ultra-high energy false vacuum. And before that sea, more inflating sea. No start, no creation event, just an infinite regress of patches bubbling out of a metastable vacuum. The impossibility here is that infinite regress violates something fundamental. If there was no first event, then there was no cause for any event. The chain of causality becomes infinite, which is logically identical to having no chain at all. What makes this particularly unsettling is that Vilenkin's own earlier work proved that any universe that expands on average cannot be eternal into the past. It must have had a beginning, so eternal inflation contradicts itself. It requires a beginning and forbids a beginning at the same time. That paradox isn't a flaw in the math. It might be a clue that our concept of before is meaningless. Number 5. The Boltzmann brane nightmare. In 2004, Sean Carroll at Caltech and Jennifer Chen at the University of Chicago proposed that our entire universe might be a random thermal fluctuation out of empty space. The math of statistical mechanics allows for this. If you wait long enough, and we mean incomprehensibly long, 10 to the 10 to the 70 years, quantum fluctuations will produce any configuration of particles, no matter how complex, including a fully formed human brain, complete with memories of a false past, floating alone in the void. The paradox is that Boltzmann branes are vastly more probable than entire universes. The math says that for every universe like ours, there should be an astronomically larger number of lonely brains hallucinating their existence. So why are we not Boltzmann branes? Why do we see a coherent 13.8 billion year history instead of a sudden flash of false memory? No answer exists within conventional physics. And that's not even the terrifying part. The real implication is that if Boltzmann branes are possible, then your memory of reading this sentence is probably false. The entire history of the cosmos, the Big Bang, the formation of stars, the evolution of life, all of it could be a spontaneous hallucination inside a brain that popped into existence 3 seconds ago and will vanish in another 3 seconds. You have no way to disprove this. No experiment can rule it out. We'll return to this when we get to number 1, because the Boltzmann brane problem might be the same problem as the origin of the universe. Number 4, the mirror universe running backward. In 2018, Julian Barber and his colleagues published a solution to the problem of time in quantum gravity. They proposed that before the Big Bang, there was a mirror universe that is identical to ours, except that time runs backward. At the moment of the Big Bang, the two universes touched. In the mirror universe, cause and effect are reversed. Entropy decreases as you move away from the bang. Our universe expands and cools, the mirror universe expands and cools in the other temporal direction. The impossibility here is that this model requires the initial state to be maximally symmetric, perfectly smooth, perfectly ordered. But we know the early universe had quantum fluctuations. Those fluctuations are what seeded galaxies. So how does a mirror universe generate those fluctuations? Barber's answer is that the fluctuations are symmetrical too. Every quantum jitter in our universe has a mirror jitter in the other universe, going the opposite direction in time. Here's where it gets disturbing. If time can run backward in another universe, then the arrow of time is not a fundamental law. It's a local accident. Something about our particular patch of reality breaks the symmetry, but that something could change. The direction of time could reverse. And if it did, you wouldn't experience your death. You would experience your birth. Your memories would unform. Every choice you made would unwrap itself, and you would not know anything was wrong, because consciousness itself would run in reverse. Number 3. The M-theory collision. In 2001, Paul Steinhardt and Neil Turok at Princeton proposed the ekpyrotic model. Before the Big Bang, two three-dimensional branes floated in a higher dimensional space. They were parallel, they were still, and then something perturbed them. The branes began to drift toward each other. When they collided, the kinetic energy of that impact converted directly into matter and radiation. The Big Bang was not an explosion from a point, it was a collision between two sheets of reality. The impossibility here is that this model requires the extra dimensions to be large enough for branes to move through them. Most string theory models compactify extra dimensions to unobservably small scales. But Steinhardt and Turok need them to be huge. There is no evidence for large extra dimensions. There is no known way to detect them. What no one talks about is what happened before the branes started moving. They must have been placed in motion by something, and that something requires a cause, and that cause requires another cause. The ekpyrotic model pushes the origin problem back one step. It does not solve it. But it does give us a beautiful image. Two membranes, vast beyond imagining, drifting toward each other in a darkness that isn't even space. And when they touch, 100 billion galaxies. And then they pass through each other and drift apart. And then, 10 to the 12 years from now, they will turn around and do it again. Number 2. The quantum nothing that was unstable. In 2018, Lawrence Krauss at Arizona State University laid out the current physics of nothing. True nothing. No space, no time, no laws, no quantum fields, no virtual particles. According to quantum field theory, nothing is not stable. The reason is Heisenberg's uncertainty principle applied to fields. Even in the absence of particles, the energy of a field cannot be fixed at exactly zero. It fluctuates, and those fluctuations can, with enough improbability, produce something. The discovery here is that the total energy of our universe appears to be zero. The positive energy of matter and motion is exactly balanced by the negative energy of gravity. This is not an approximation. Measurements of the cosmic microwave background and the expansion rate put the total energy density at zero within measurement error, so the universe could have come from nothing without violating energy conservation. The paradox is that nothing is a state. It has properties. It has stability, or rather instability. Nothing wants to become something. It's not that something came from nothing. It's that nothing is the most unstable state there is. Given infinite time, nothing will always produce something. But here's where it gets disturbing. If nothing is unstable, then the only stable state is something. Which means the natural state of reality is not emptiness. It's a universe. Our universe isn't an accident. It's the equilibrium condition. The nothing before our universe wasn't a calm void. It was a ticking bomb. And the ticking was the universe trying to exist. Number 1. The observer who cannot not exist. All of these theories share one problem. They all assume that time existed before the universe. They assume a before in which something happened, branes collided, nothing fluctuated, a quantum foam bubbled. But in 2007, Raphael Bousso at UC Berkeley proved a theorem in quantum cosmology that the probability of a universe like ours existing requires a measure. And that measure cannot be defined without an observer. Here's what that means. To question what existed before the universe assumes a timeline. It assumes that before is a meaningful direction. But if time itself began at the Big Bang, then the word before has no referent. It's like asking what's north of the North Pole. There is no north. There is no before. The paradox that shatters every model is this. You are asking the question. Your existence as an observer collapses the probability wave of possible pasts into one actual past. The universe before the Big Bang is not a place you can describe because you are inside the description. You cannot step outside of causality to examine causality's origin. The loop closes here. Number 6 asked about infinite regress. Number 5 asked if you are a Boltzmann brane. Number 9 asked about information surviving the death of a universe. All of those questions have the same answer. They require an observer outside the system. And there is none. The most disturbing implication in all of physics is not that the universe came from nothing, it's that the question itself is illegal. You cannot ask what came before time, because the asking creates time. You are the beginning. Your consciousness, your observation, your existence, as a pattern of information that can ask about its own origin. That is the only before that matters. The universe is not old. The universe is not young. The universe is the present tense of a question that has no past, and you are the one asking it. If you want to see more videos like this, click the video on screen now and make sure to subscribe.